Last video we looked at what standard electrode potentials were. Earlier in this topic we've also done an experiment where we made a cell using the zinc half cell and the copper half cell. So our anode was zinc and our carbon was our cathode. And we got a positive voltage for this. A lot of us got a value that's going to be a lot bigger than the value we got. Our copper one was our cathode.
Oh, you said carbon.
Oh, I say carbon, sorry. Copper was our cathode. So, now that we know what standard electrode potentials are, and we have seen an experiment where there is a voltage created, which is actually our electromotive force of that cell, we can see how those two ideas come together. As well as that, the result you got in your experiment was not the same as the value we'd get by doing it through the standard values. And that's because the conditions you were using were not standard. So there are other things happening that really can't be accounted for with what we had. Right, so if I have a look at a data table and you'd be given this information, the electrode potential for the zinc half cell is negative 0.76. It's negative, so I know it's a reductant. So it's probably going to go on the left-hand side where oxidation occurs. The copper half cell, not the carbon one, thank you for correcting me, has got a positive value, positive 0.34. So I would guess that it goes on the right-hand side because it's an okay oxidant. It's going to be reduced. It's going to undergo reduction. So setting this up, anode, my bridge, then cathode. I've got my values, so what do I do with it? To find the electromotive force of the cell, or the standard electrode potential for the cell, if you want to think of it that way, I go the right-hand electrode's electrode potential, or reduction potential, minus the left-hand electrode. So when you see these little subscripts, RHE and LHE, they mean right-hand electrode and left-hand electrode respectively. So you might see those in books and go, what does that mean? There you go. Now I don't need to worry about changing signs or anything like that. The minus accounts for that already. Really what you're doing is finding the sum of the potential difference of voltage in the cell to find how much voltage it can make. This is just, it's easier to remember that EMF is right-hand electrode minus left-hand electrode. Okay. So, the right-hand electrode we've decided is copper. I'm hoping like heck we've got it right. So I put my positive 0.34 here. I put my negative 0.76 here. So it's 0.34 minus negative 0.76. And so I get a value that is positive 1.10 volts. And some of you got much higher than about 1.5 volts, some of you, which is very high. That will probably be due to impurities in either your solution or on one of your electrodes or both of your electrodes. So that's why you didn't get 1.10 volts. Okay. We did it at about 25 degrees Celsius. We did give you 1 mole per litre solutions, so we kept the other things correct, but our purity was almost certainly our problem there. Okay. The word we use there is one we've met many times before. This means, because it's greater than 0, this means it's spontaneous. That means it goes the way that I've drawn it, where this is the anode and this is the cathode. It means the electrons are flowing from the zinc to the copper as part of that cell working. It means that oxidation is occurring here and reduction is happening here. When you're assessed on this, you're going to be asked to say what you would observe. So you would observe, if you had it running for long enough, that the zinc would get smaller as it's oxidizing, turning into zinc ions. The copper electrode would be getting bigger over time, fatter and bigger, as the copper ions are deposited as copper metal. The blue copper solution will fade in colour. The blue colour will start to fade as it's probably going to be potassium ions from the salt bridge go across to complete the circuit as that becomes the solid. And you wouldn't observe this apart from the fact that it's going to be a positive voltage on your voltmeter, but the electrons are flowing in the direction you would expect, from anode to cathode. Now, if I had drawn this back to front and not realised that zinc was going to be the anode and copper was going to be the cathode, if I'd gotten the other way around, then I'd be going negative 0.76 minus positive 0.34, and I'd get a value of negative 1.10 volts. If it was negative, it would mean that oxidation is actually occurring on the right-hand side and reduction is happening on the left. So that would mean that our observations were the opposite to what we'd see for oxidation and reduction. So if you get a negative value, it means you've done the cell diagram incorrectly. However, it's still worth saying it's negative, so it's not spontaneous. That means, not that it doesn't happen, it means it's the opposite. The electrons are flowing in the opposite direction, and you'd observe the oxidation occurring there and the reduction occurring there. So that's why it's important to do these, to find whether it's a positive or negative value. You then link it to the word spontaneous. If it's not spontaneous, it means electrons are flowing backwards, so from the right-hand side to the left-hand side, and that you'd observe the oxidation on the side and the reduction on the side, if it's a negative voltage. If it's a positive voltage, it means that you made your prediction correctly. So observation would be oxidation and reduction here, and you're going to have the electrons flowing from the left-hand electrode to the right-hand electrode. That's why these values are important. Now, when you calculate them, they will be different to the values you get experimentally. And because there's an internal component to this assessment, you need to be able to justify that. Because it's likely to be about 25 degrees Celsius when you do it in the classroom, you can't use that as a reason. We're at sea level, so atmosphere is going to have very little to do with it too. And we're going to give you 1 mole per litre solutions. So that's going to have nothing to do with it. Therefore, the only valid reason you can talk about are impurities, either in the solutions or on the cathodes. On the electrodes.